two sources of waves. We're getting our interference pattern that's been caused by this, and as you can see, I get my destructive interference taking place as I go along here. I get destructive interference taking place, then I get my constructive interference, then destructive interference, then constructive, then destructive, then constructive. So if I drew this up here, if I drew a graph of my amplitude of my waves, I'd get something like this. I'd get like this. Something, it would be a much nicer diagram, but anyway, it would be something like that. Alright, where you're getting your maximum and your minimum. So you're getting your minimums, your maximum, you'll get that sort of graph. Alright, that's what happens when you've got two sources interfering with each other. Now, when we had a look at the laser going through a double slit, we had that sort of effect, didn't we? Because I think you saw that we had something like this. You had lots of these little, let me use it was red. Let me use red. So you had lots of these ones all the way along, didn't you? But you had something else that seemed to be on top of it. So this would be your minimums and your maximums occurring. But there was something greater, something else that was modulating that whole thing. Now basically what happens is you get this effect. But what takes place, so if I just bring this down over here, actually I've gone a bit far. This is what I was just drawing now. This is your intensity, this is your maximum, minimum, maximum, minimum. So you get this shaped graph. But because it's going through a slit, and because each one's going through a single slit, you get the single slit diffraction that gets superimposed on that. So you get this situation over here. And this is what we saw. Alright, you get, this is caused by we call this a diffraction envelope. This is caused from the single slit. Slingle. What's that? I'm glad I didn't do the spelling bee. The single. I wouldn't have been able to spell one of those words. Single slit. So the single slit causes this over here, like that, and these over here were these little lines that you saw, the little ones in between. This is caused by the double slit, so it fits through. So you get this sort of situation taking place. Alright, I think you saw that quite nicely there. So this is the graph for double slit diffraction, where it comes. So you actually need to draw this. So what I would do if I was you, really, I would cut and paste that into your notes. Alright, because you'll probably find it'll be much easier to learn from that than it would be from a hand-drawn diagram that may cause you more problems than anything else. Okay, so except for some of you, not all of you, but for some of you it's like that. Okay, so that's our double slit. Now, what it was found is that when you have this, now if you have, for instance, our eyes are an aperture, are an opening to allow light in. Now what happens is that you get diffraction taking place, and so you get this sort of situation taking place. So if I've got two sources of light, this is light 1 and light 2. This could be the headlights of a car, alright, from far away. Now what's happening is that you've got, you've maybe got over there, you've got your headlight 1, you've got your headlight 2, and they are beaming out light. And you've got your eye at a certain distance away. Obviously this is exaggerated, but the light is coming through there and it's going into your eye, and there's diffraction that's taking place, and it's coming onto the back of your retina. And now your eye, if it's a certain distance away, can actually distinguish between those two. Alright, it can see that you've got two lights. Now there was a chap called Rayleigh, and he came up with this idea of when it would happen that you could no longer resolve between two things. This would be resolved. This would be fine. This over here would still be resolved, still be able to resolve it, even though it's getting pretty close. You see, here's your principal maximum is there. This is your one principal maximum, that's your other principal maximum, but still you could resolve it, still resolvable. This is the cutoff point over here. This is the Rayleigh Criteria, and basically what he said was when the principal maximum of one of the sources is in the first minimum of the other, it is just resolvable. So when S1, if I drew S2 here, S2 goes like this, and it goes out and it does that, you see? So this is the principal, this is the first minimum now of S2. When the principal maximum of S2 is in the minimum of principal maximum S1 is in the minimum of S2, it is just resolvable, and this is called the Rayleigh Criteria. All right. Yes, straight down. So let me do it with this one over here. So for instance, I can't draw very straight lines here. If that intersects the minimum of that, then you're just going to be resolvable. And this is the Rayleigh Criteria. This is if you go over here, if you go to this over here, it says state the Rayleigh Criteria for images that are just resolved. Okay, you need to know that. Now there is a formula, and let me just sorry, Zibnet. Okay, let me. I'm going to bring up a formula for you here now. The formula is in your data booklet. Let me just bring it in here, up here, so that you've got it. This is the formula over here for the Rayleigh Criteria. This is the formula that we had just now. This is for the single slit diffraction. But remember, you've got to be able to extend that a bit more. This is a Rayleigh Criteria, and again it says theta is equal to 1.2 lambda over b. Now I'll just explain what each of those terms are. The b, this could be for anything like for a telescope or for a microscope or for the pupil of one's eye. This b over here is the aperture diameter. Aperture, is that right? Diameter. It's that distance there across. That's b. The lambda is the wavelength of the light. Is the wavelength that we're looking at. All right, the wavelength of the light, and the theta is the angle between the two sources. So if you've got, for instance, here S1, S2, and you've got like that and like that. I haven't drawn this very nicely, but anyway, that's the theta. That's the angle. Now, if this angle, if you work this out, all right, and you get a certain angle, we call that theta. If the angle is greater, if your angle is greater, so let's call it beta, all right, if the angle that we have is greater or equal to theta, then then it is resolvable. Beta is the actual angle that it is. So you can, for instance, here, let me redraw this, sorry, let me do this again. So you've got your two sources of light. Alright, so you've got your two sources of light. Alright. and you've got them coming through, and they go through some aperture, whatever it is, with a certain b value. Certain b value. This is S1, S2. There's a certain lambda. And when you measure this, you measure it as beta. Alright, so this is the measured value. Alright. You can calculate. You calculate theta just from knowing this aperture and the lambda that you're dealing with. You can calculate theta, and if beta is greater or equal to theta, then you know that it's resolvable. Does that make sense? So for any aperture, for any telescope, alright, you may have a telescope and say you're working with yellow light, maybe 600 nanometers, alright, and you've got a telescope with a certain aperture, maybe it's 10 centimeters, alright. You can work out from that the theta, or the angle that you will be able to resolve objects from. So let's just take an example. Let's just say let's just take your wavelength is equal to 600 nanometers, alright. So that we know what that is. That's 600 times 10 to the negative 9 meters. And let's say you're dealing with an aperture of, say, 10 centimeters. So it's going to be 10 to the negative 1 meters. Alright? Then you can put it into this formula. Theta is equal to 1.22 times 600 times 10 to the negative 9 divided by 10 to the negative 1. Yeah, so lambda. So this is lambda. It's the size of, it's the diameter of the aperture that your light is coming through. All right. So any sort of optical instrument has got a diameter that it allows. So for that, 10 to the negative 1, obviously that goes up, becomes positive 1. Let's just simplify this down. Let's just take that out. So that's going to be 10 to the 8. That's going to be 10 to the negative 6. So that's going to be 6 times 10 to the negative 6. All right? Radians. That this angle can be, that you'll be able to distinguish between those two things. That's the smallest the angle. So obviously bigger is fine, but that's the smallest you can go to. All right. Now that's you can see that's very small. So one is able to distinguish with optical instruments to very small angles. All right, that difference. And I mean, you just take for yourself. You just take for yourself. I mean, if you take, for instance, a car coming, maybe it's 1 meter between each other, those lights. How far away do you think you can start to distinguish that there's two lights, not one light? That you can distinguish. Just distinguish. Remember, we're just resolvable here. You can just say, oh, this is not a motorbike, this is a car. Alright? A kilometer? Here? What do you think? Perhaps a kilometer. Let's say it's a kilometer. So it's 1,000 meters. Alright? So the theta is equal to 1.22 times the wavelength of light. Well, I mean, just in this case over here, we don't really need to use that. We've got 1,000 meters, and we've got there, we've got 1 meter. Now, because tan and I mean, this becomes pretty. You basically got a 1 over 1,000th value there. And if you find the tan of that, it's like a 10 to the negative 3 radians that you've